Now for a specific use of differential equations, position, velocity, and acceleration, aka PVA. Which right now you may be saying to yourself, not physics, I don't want to do physics, but unfortunately all physics is applied calculus, so we'll do at least some physics in here. So if you have a function that gives position, x of t, then when you differentiate that function, it gives you velocity, because velocity tells you how fast position is changing. Like if your velocity is 15 feet per second, you're going 15 feet every second. And acceleration is the derivative of velocity, which is the second derivative of position, because acceleration tells you how fast velocity changes. If your acceleration is like 10 feet per second squared, that means that every second you're going 10 feet per second faster. Right? So 10 feet per second squared. How this relates to differential equations is because sometimes acceleration is constant. So if acceleration is constant, and an example of this, by the way, is cases where you have an object under the influence of gravity, where you're ignoring wind resistance, because gravity provides a constant acceleration to an object, as long as you're within a certain range of the Earth. So the acceleration due to gravity is negative 9.8 meters per second squared, or, if you prefer feet, which probably none of you do, negative 32 feet per second squared. That is the acceleration due to gravity if you ignore wind resistance and all that fun stuff that makes reality real. But if acceleration is constant, then you start off with that. Acceleration is a, where a is the constant. And to find the velocity function, you would integrate that. That is a differential equation. You would integrate that, and it gives you at plus v naught, where the v naught is your plus c, v naught is your initial velocity. And to find your function for position, you would integrate that. So at integrates to 1/2 at squared, v naught to v naught t, plus the constant, which in this case is x naught. That is your initial position. You won't have to know these for a quiz or a test or anything, so don't worry about trying to memorize them, but you might recognize these from physics. A lot of your equations from physics are just these equations written differently. It's just variations of those equations. But let's do an example where we have a constant acceleration. It won't be gravity though. Let's instead do a question about like a car accident scene maybe. So for example, let's say you have some car and you know that the car screeched to a halt and that the brakes were applied for 160 feet, which you can tell from the skid marks on the street. And when you test this particular car in a controlled environment, you find that when the brakes are fully applied, there's a constant deceleration, which is a negative acceleration, of 20 feet per second squared. So at full brake, you go 20 feet per second slower every second. The question is, how fast was the car going when the brakes were applied? So there's the question. You know from the skid marks that the brakes were applied for 160 feet before the car stopped. There's a constant deceleration of 20 feet per second squared that you got from testing the car in a controlled environment. And the question is, how fast was the car going when the brakes were applied? So, this is a case where we have a constant acceleration. And the acceleration function here is negative 20. Negative because it's deceleration. The car is losing 20 feet per second every second. And we use this to find the velocity and the position functions. Negative 20t plus v naught. We don't know v naught. That is the point of the question. And then we integrate that to find x of t. Negative 10t squared plus v naught t plus x naught. Now, x naught is your initial position, which is often arbitrary. It's up to you, the person doing the question, what you want to call 0. Now, it makes sense to call the point at which the brakes were applied 0. So our initial position, x naught, we'll call 0. It's by our choice, which means x of t is just negative 10t squared plus v naught t. Now you figure out how to use these equations. For a question like this, it's always smart to start by finding a, v, and t as much as you can, and then figure out what else does our question tell you. How can you use this? Well, we know that there's some time t such that the car has finally stopped after going 160 feet. So I'll call that t1. So at time t1, this is when the car has finally stopped, which means x of t is 160, because that's how far the car went before stopping. And v of t1 is 0, because after this unknown time it takes to stop, the car has finally stopped and it's gone that far. So time t1 is as the car brakes, it finally stops. And so we write down those equations. X of t1 is 160, means negative 10 t1 squared plus v naught t1 equals 160. V of t1 equals 0, gives you negative 20 t1 plus v naught equals 0. And now we have a system of equations. And you can solve this however you would like. The way that I'll solve it is I will solve this equation for v naught. So v naught equals 20 t1. And then plug this into that v naught. So negative 10 t sub I squared plus 20 ti times ti equals 160. That gives you 10 t sub I squared equals 160. Solve that for t sub I. You get t sub I squared equals 16. T sub I equals 4 seconds. Now I made this question up to have a whole number answer. For the final, I would do the same thing. I would make up a question that has a whole number answer. Same for the midterm. For the P sets though, I won't. For the P sets, I'll just make up stuff, and it's okay if the answer's all irrational. But for this one, I made it to be 4 seconds. But the question's not how long did it stop. The question says, how fast was the car going? So we plug this back into here, v naught. So 20 times 4 is 80. And then make sure that you know what your units are. We have 80 feet per second. So when the brakes were applied, the car was going 80 feet per second. Which you can figure out how fast that is. I think 80 feet per second is like, I don't know, like 50 some odd miles an hour. Let me do the math real fast on my calculator. It's 54.5 miles an hour. .545. So then you, as the scene investigator, would figure out if that was over or under the speed limit for that specific street. And this is kind of how they can use the skid marks from a car to figure out how fast the car was going. Measure the skid marks, find the deceleration rate when the brakes were fully applied, and then do the math out to see how fast the car was going. Okay.